Good evening and welcome to part one of a two-part series that I have put together for Kent County's SKYWARN, looking at Kent County tornadoes. Firstly, looking at the history, the trends, and the data for Kent County tornadoes over the last several decades, and also more specifically looking at the radar signatures over the last 20 years for tornadoes that have impacted our county. So, to begin, first of all, before we dive into all of that, doubtless some of you who are listening to me, whether during a live lecture I might give in the future, or perhaps during the YouTube recording that you are now listening to or watching, as the case may be, my name is Colin McConkey. I am a ham radio operator. My amateur radio call sign is KE8RXN. And for those of you who do know me, you know that I love ham radio and I also love Skywarn because that combines two personal interests of mine, specifically emergency communications and also weather observation and reporting. Now, this presentation, in fact, this two-part series will not really pertain specifically to ham radio, although that would certainly be very enjoyable to do a 2-hour series or so on ham radio, if not longer. But rather, this pertains specifically to Skywarn, which is the amateur storm spotting community that gathers live weather data and reports it to the National Weather Service forecast offices throughout the United States in order to better assist them in monitoring real-time weather conditions and also preparing watches, warnings, emergencies, as the case may be. So all that to say, doubtless many, if perhaps not all of you who are listening to this are ham radio operators like myself. And for those of you who may be interested, I am a licensed amateur extra ham radio operator. But as I said, this will not pertain specifically to ham radio. But you might ask the question, all right, so you're an amateur extra ham radio operator. You're a member of Kent County Skywarn, but what specifically drew your interest to tornadoes? Well, tornadoes have always been personally fascinating to me, specifically after the monumental El Reno tornado on May 31st of 2013. I was not a ham radio operator in 2013. I was not a Skywarn spotter in 2013, and truth be told, I didn't really pay all that much attention to the weather here in West Michigan in 2013. I've grown up in West Michigan my whole life. I know the weather patterns certainly, as all of us do who have lived here for some time. We tend to get a little bit more extreme temperatures here in the sense that we can get very cold winters and very warm summers. So we're not necessarily a super moderate climate, but thankfully, truly severe weather, really severe weather, earthquakes, really bad tornadoes, tsunamis, all of those things, thankfully, generally escape us here in the West Michigan area. And I'm certainly grateful for that. But you would be surprised. Some of the weather that we're going to be looking at this evening really did impact our county and our West Michigan community in some bad ways, in cases where there were not sufficient warnings given or where the warnings were not heeded. We see the cost, sometimes even of life and limb, that will bring. And when those warnings were heeded, when they were improved over time, we really see the advantage that those play in protecting our communities, our friends and families who live in these areas from the impact of severe weather. So, as I said, ever since the El Reno tornado struck in El Reno, Oklahoma on May 31st of 2013, is captured in various Weather Channel, National Geographic, Disney Plus, Discovery Channel documentaries at the time, I've been fascinated with tornadoes. Now, I should add, I am not a professional meteorologist. I'm not a professional climatologist. I'm not a meteorology student in the sense that I'm not a formal student of the field as my actual academic credentials lie in a separate field other than meteorology. So, with that having been said, I am an amateur weather enthusiast doing my best to improve my overall knowledge of meteorology, of radar observation, of emergency communications, and the like. So, with that, if you happen to notice anything that is factually incorrect, please feel free to let me know. Feel free to contact me at my email, which is posted on qrz.com for those of you who are ham radio operators. For those of you who are not, just feel free to leave a comment in the YouTube section below and I will try to respond. My effort is not certainly to do the work of a professional meteorologist, as I am not that, but rather just to encourage fellow amateur weather enthusiasts and SKYWARN members in my county and perhaps even surrounding counties, depending on how wide a reach this series gets, to just strive for greater standards of excellence and more accuracy with radar observations. So please feel free to let me know of any corrections that you see I might need to make in the future, or just any general questions or comments that you may have about the data or about the series in general. I would be more than happy to hear your feedback. So, looking at part one of this two-part series, we've already covered the personal introduction, so I won't repeat that. And then I'm also briefly going to go over my three primary data sources. I know oftentimes, whether writing academic papers, of which I've certainly written many, and I'm sure some of you listening have written many as well, or whatever the case may be, oftentimes you'll see references, footnotes, etc., listed at the end of a presentation. I'm actually putting my three main sources at the beginning. And the purpose is so that way you know right up front where I'm getting my data from. And also, not only so you know where I'm getting it from, but that way you can actually take these sources and do your own research. And I would highly recommend you do that. You can take the same radar files, the same historical NextRad data that I utilize, especially in part two when we get to part two, and do your own studies. And I would really encourage you to do that because it's really fascinating. And you may uncover things that I may not have included or may not have observed or thought about. And if you do, awesome. Feel free to let me know what you find out. This is a team sport, it's not a solo sport. So, after we briefly look at the three primary data sources that I have used to collate all the information here, we're then in part one going to look at a brief history of radar, a brief history of the National Weather Service, an introduction to tornadoes, which doubtless some of you will know, but nevertheless, I think a refresher is certainly helpful. And for some of you listening, maybe you aren't as familiar with tornado genesis, how tornadoes form. And then we're going to look at data that I don't believe really gets the light of day hardly at all here in our West Michigan community, which is looking at the exact numbers, the exact trends, the exact data for the history of Michigan tornadoes statewide, briefly, the history of tornadoes within the Grand Rapids National Weather Service County Watch forecast area, and I'll clarify what that is when we get to that point, and also, of course, specifically our primary area of interest, which would be Kent County tornadoes, as this is geared specifically for Kent County. Although I do hope that if other SKYWARN members in surrounding counties are listening to it, that you can glean a lot of useful information as well. And so when we look at the data sources, I will actually add you can take all of these data sources and do the exact same study for your county that I am doing now for my county here in Kent County, Michigan. So the first primary data source would be the National Oceanic and Atmospheric Administration's National Centers for Environmental Information Storm Events database. Secondly, it would be NOAA's National Centers for Environmental Information Historical GR Level 3 NextRad radar data. And if you aren't familiar with what that means yet, don't worry. I will cover what NextRad radar is and what also GR Level 3 is. And finally, and very importantly, I think for any weather enthusiast, especially SKYWARN spotters, the Historical Storm Prediction Center convective outlooks. And in looking at those specifically, I did my best to find the most recent day one convective outlook right up to the moment that the tornado in question struck our county in order to get the most accurate convective outlook information, tornado probability information, and so forth. And again, I'm sure many of you know what the Storm Prediction Center is and convective outlooks are, but for those of you who don't, we're still going to cover that once I get to that point. So, to begin, let's look at a broader level the history of radar and the history of the NWS, or the National Weather Service. Now, if you were to ask an amateur radio operator or a SKYWARN spotter or perhaps maybe a meteorology student or someone in technology or whatever the case may be, when did radar really begin in the United States or really in the history of the world for that matter. A lot of times people will tell you, well, it goes back to the two world wars used for first locating ships and then for locating aircraft. And yes, that indeed was the impetus that caused radar to take off and later on through false positives, which we'll talk about in a moment, being utilized to discover precipitation on radar and convection. But in reality, I believe that the history of radar goes all the way back to the 1880s. In 1886, a physicist by the name of Heinrich Hertz, and for those of you who are ham radio operators, you'll immediately recognize his last name, Hertz, from which we get our unit of frequency, observed that objects reflected electromagnetic waves. Now, again, for those of you who are ham radio operators, you know that electromagnetic waves are radio waves. And for those of you who are not ham radio operators, you can see in the diagram in the lower right of the slide, you can see that electromagnetic wave. You can see that the electrical field component is vertical and the magnetic field component is horizontal. So that 3D electromagnetic wave is a radio wave. But far beyond simply what we think of in terms of radio, whether FM radio or AM radio, but everything on the radio spectrum, everything from visible light to infrared to ultraviolet to various types of ionizing radiation used in medicine for which people need to take precautions not to be overexposed to. A radio wave is simply an electromagnetic wave. And so what Heinrich Hertz realized, what he discovered in 1886 is when you bounce a radio wave off an object, it'll bounce back. You can think of it because this is exactly the same way, just in a different part of the radio spectrum from what we think of traditionally as radio. A flashlight, the beam of light, is arguably a radio wave in the visible light spectrum. And when you bounce it off an object, what does it do? It bounces back. Now, even if you aren't necessarily aiming it at a mirror where it's bouncing right back to you, you still will have that flood of light illuminating whatever you want to illuminate. And just like a flashlight, you can you can picture a lantern where you have this wide spill of light in basically every direction in 360 degrees, or you can take a flashlight as opposed to a lantern and concentrate those visible light radio waves into a very tightly focused beam. That's what Heinrich Hertz discovered in 1886. And so, about 20 years later, a German engineer was granted a patent for using these electromagnetic waves, these radio waves, to detect obstacles and to aid in navigation for mariners. Obviously, a mariner, a captain of a ship, or anybody traveling on the seas, or even the lakes or rivers or whatnot, if you can't detect other maritime traffic, if you can't detect barriers that might damage your ship or possibly halt or end your navigation, that's not a good thing. Running aground is certainly never a good thing. Colliding into another ship is certainly never a good thing, no matter what time of history you're living in. And so in 1904, there was a German engineer who was granted a patent for trying to use these radio waves to detect other ships at sea. It wouldn't really take off, as I mentioned, even though it had been in development, as a lot of technologies sometimes are. It went viral, so to speak, to coin a modern 21st century 2022 phrase. But in 1922, going back 100 years, through the end of World War II, scientists worked to implement this idea, this technology, to detect enemy ships at sea, and later on, especially in World War II, enemy aircraft. Because you could obviously aim these radio waves not just straight out at a horizontal plane towards the horizon, you could also aim them whatever direction you wanted. You could aim them straight up into the sky in order to detect aircraft. And so pictured in the upper right of the slide, you can see what by our standards would certainly be a primitive radar station, but you can see a World War II radar station in the upper right. Now, here's what's fascinating, and here's really the breakthrough that really cemented the future of radar when it came to meteorology. During World War II, radar observers, who of course were trying to look for enemy aircraft, found that precipitation in the atmosphere would generate false positives when attempting to detect these aircraft, like I said. So these false positives on radar, this precipitation, all of a sudden, they realized, hey, we can actually sort of detect the weather using radar. And enemy aircraft actually would pick up on this concept as well too. Aircraft would often use strips of metal flying off the back of the plane called chaff in order to confuse radar observers because they knew that this would generate false positives for them. But a side effect, as I said, of that wartime technology was the ability to detect precipitation, convection on radar. And so the United States Navy and the United States Air Force, through the end of World War II, through the 1950s, up through the 1960s, they would continue to develop this radar technology. And eventually, in the 60s especially, I believe around 1965, at least in the mid 60s of that, I'm certain, would eventually be adopted by the National Weather Service. Most original radar equipment used by the National Weather Service, in fact, was actually repurposed wartime radar equipment. So that segues us further into the history of radar, where we go all the way up into the more modern era in 1998. Now, in 1998, NEXRAD, which is next generation radar. And you may chuckle and think, well, 1998 technology is not really next generation anymore. Nevertheless, at the time, it certainly was. In 1998, NEXRAD was developed in a joint effort by the Departments of Defense, the Departments of Commerce, and the Departments of Transportation. By the early 1990s, NEXRAD radar stations covered the United States, and we still use these today by the National Weather Service. Now, we could get into discussions about like dual polarization radar, which if you've taken SKYWARN classes, you've learned about to some extent. They can do really cool products like correlation coefficient and other more advanced radar observational products. But suffice it to say, NEXRAD radar, it's still utilized even though it's a technology from the late 80s, and it's what we're going to be looking at, especially in part two. Now, for those of you who are ham radio operators, NEXRAD radar utilizes the 10 centimeter band, which is known as the S band, which is utilized by air traffic control, weather stations, NASA, such as when NASA is talking to the International Space Station, and others. Now, this being in the 10 centimeter band, of course, is in the very upper limits of the UHF portion of the radio spectrum around 3 gigahertz. Now, I will add a disclaimer that there have been different frequencies and different bands utilized over time by radar. So I'm not necessarily stating that your local weather forecast office is using a 3 gigahertz radar, but nevertheless, that's predominantly what NEXRAD radar is. It's within that 3 gigahertz frequency, that 10 centimeter wavelength. So GR level 3. That is a radar program. It is the official radar program of Kent County. While there have been newer radar programs since GR Level 3s, there was also GR Level 2, its predecessor. There's GR Level 2 Analyst, which is the top of the line radar program, which is very expensive. It's about $300 to purchase. It does 3D modeling for you. Suffice it to say, even though the GR Level 2, 3, 2 Analyst, whatever you want to call it, programs have been out for some time and there have been newer ones, they are still exceptionally good. They are very good and they are the official radar programs for my county. So that is what my source of truth is when it comes to radar for my county. Now, I also, for those of you who might be curious, heavily rely on Radar Omega, which has some more modern features that GR Level 3 does not. But at the end of the day, like I said, GR Level 3 is the radar program that I use, that I watch the most, and that I will rely on when it comes to severe weather signatures. And everything that we see in part two is directly taken from GR level 3 historical NEXRAD data. And we'll get to that in part two. And in case you were curious, all of this data, in case you didn't catch it in the beginning, can be downloaded from NOAA's National Centers for Environmental Information historical NEXRAD radar database. So, concurrent with the history of radar, we also, of course, need to discuss the interesting history, albeit briefly, of the National Weather Service. Now, the history of weather observation really goes back to the history of humanity, I suppose, but specifically in terms of what the historical precedence was for the SKYWARN programs, it really goes back all the way to our nation's founding. And I say that because many of our founding fathers, famous ones in fact, such as George Washington, Thomas Jefferson, would routinely record and observe the weather measurements throughout their lifetime. In fact, I believe it was George Washington who kept on recording the weather, the daily weather, until shortly before he died. And in fact, some of these founding fathers were scientists who did weather experiments in order to further advance meteorology, such as it existed then at that time. So, the United States of America being founded after the Revolutionary War, being ratified with the adoption of the U.S. Constitution in 1789, now an official country recognized by other countries, in the early days of U.S. history prior to the Civil War, the Smithsonian Institute would receive reports from weather observers throughout the United States. And this was the bread and butter for Smithsonian creating weather maps based on telegraphic reports up through the time of the Civil War. So basically, an official institution, the Smithsonian Institute, would take weather observations, weather reports by telegram back then, once telegram technology came along, and use it to create weather maps. Now, the National Weather Service doesn't have to rely solely on those reports now, of course, to forecast weather. We have very sophisticated products and technologies that certainly go beyond my current understanding of meteorology and forecasting, although I'm certainly doing my best to improve that knowledge. But nevertheless, we still play a vital role in assisting the National Weather Service in observing live weather conditions. And prior to all of this technology in the 20th and 21st centuries, it was even more important because that was the basis for how scientists, weather forecasters, meteorologists knew what was going on throughout the United States. 5 years after the Civil War ended, former General Grant, of course, then at the time President Ulysses Grant, signed a law on February 9th of that year. February 9, 1870, President Grant would create a National Weather Service. And by 1890, this would be known as the U.S. Weather Bureau. Now, as we're going to see here in this short history of the NWS, the Weather Bureau, the historical name, the former name for what would become later on known as the National Weather Service, would be juggled around from different federal from different executive agency to different executive agency, but in the beginning it existed under the umbrella of the Department of Agriculture. And so by 1900, the turn of the 20th century, the Weather Bureau was already forecasting weather, and it would issue weather warnings to alert the public to impending severe weather. Obviously not as sophisticated as what we have now, and of course without the use of radar technology, certainly limited in its application. By 1940, the Department of Commerce took over the Weather Bureau from the Department of Agriculture. 3 years after the end of World War II, in 1948, United States Air Force meteorologists did something remarkable and something that set a precedence that is still being done to this very day, which is in the state of Oklahoma, from Tinker Air Force Base, which to my knowledge is still a current active Air Force base used by the United States Air Force. They issued the first tornado warning in 1948. Now, why is that significant? Firstly, because it was the first tornado warning ever issued, and secondly, where is the Storm Prediction Center located? It's located in Norman, Oklahoma. So while Tinker Air Force Base and the SPC are not one and the same thing, I just find it fascinating historically that that is where that area of the country is where the first tornado warnings were generated, and the SPC, of course, is based in that same area of the country to this day. Once we get into the mid 1960s, in 1965, the Department of Commerce, which had seen oversight of the U.S. Weather Bureau for 25 years at that point, created the Environmental Science Services Administration, or the ESSA. This, of course, would incorporate the U.S. Weather Bureau at the time, and 5 years later, in 1970, the ESSA would become NOAA, N0 or NOAA. the National Oceanic and Atmospheric Administration, which of course is what it is still known as today. And in that same year, in 1970, the U.S. Weather Bureau would become what we call it today the National Weather Service, or the NWS for short. Now we fast forward 19 years. I had mentioned this briefly in the history of radar previously, but when we fast forward 19 years in 1989, we see that a 10-year 4.5 billion with a B, $4.5 billion plan modernizing the NWS got underway at the time. And of course, as I had mentioned during the brief history of radar, the predominant idea was to build and to utilize NEXRAD radar stations throughout the United States in order to better observe and forecast the weather. Now, when it comes to our local forecast office here in Grand Rapids, Michigan, we actually have to briefly go back all the way to 1903, in which the U.S. Weather Bureau, as it was known, of course, at the time, established a WFO, or a Weather Forecast Office here in Grand Rapids, Michigan. 31 years later, in 1934, an airport office was created adjacent to the Kent County Airport. And this is something you still see today. You will still see radar stations adjacent to airports, and in fact, in big major cities. Detroit has one, for example. Chicago, I believe, has a couple. Milwaukee has one. A lot of these really big major cities throughout the United States will have their own separate radar station that is for a smaller area to obviously serve as a backup to the larger National Weather Service radar station, but of course more closely observe radar conditions specifically for their air traffic coming in and out of these large urban airports. So in 1934, that airport that was created adjacent to the Kent County Airport would eventually become known as the National Weather Service in Grand Rapids, Michigan. And it still operates today adjacent to the Gerald R. Ford International Airport. And what's interesting, actually, as a quick personal anecdote, I actually had the privilege to watch President Ford, I believe in 2000 was the year. I was able to watch President Ford christen what was formerly, as we always knew it, the Kent County Airport to the Gerald R. Ford International Airport. Yes, it's international because it flies to Canada, which still counts as DX for those of you who are ham radio operators. I'm not aware if it flies to any other international countries currently, but perhaps. But nevertheless, that weather forecast office, established in 1934, still operates to this day to the current airport here in Kent County, Michigan. So that covers the history of radar, the history of the National Weather Service briefly. Certainly, we could talk about these to much greater length, but let's get on to the thrust of the presentation, which is tornado genesis. Introduction to tornadoes. Tornado genesis being how tornadoes form. Now, I will say that I'm not going to cover convection at a basic level or thunderstorms at a basic level in these two-part series. I'm presuming that you already know what convection is. You've got warm air rising and then cooling and then coming back down. And with that, it can bring a lot of wind and a lot of rain and in some cases hail. In the most extreme cases, you can have tornadoes. That's really oversimplifying it, but that's at a very basic level how thunderstorms form. But we're going to specifically be looking at tornado genesis, looking at a component of convection, which is wind shear. Now, what is wind shear? Wind shear is essentially where you have crosswinds at different elevations, different heights in the atmosphere, creating rotation in the atmosphere. Essentially, when you have rotating columns of air extending up from large cumulonimbus clouds. Now, again, I'm presuming that you know what your clouds are, but for those of you who might not know, cumulonimbus clouds are your towering thunderclouds. You know, your cumulus clouds are your light, fluffy clouds, but your cumulonimbus clouds, those indicate strong updraft that can, of course, produce severe thunderstorms or even supercells with enough wind shear and the right components can obviously produce tornadoes. But nevertheless, when you have those cumulonimbus clouds, when you have rotating columns of air produced by different directions, different strengths of wind, many times at that upper layer of convection, you have far stronger winds than you do at the lower layers. So you have shear or you have spin, you have rotation being generated. And as you can see in the upper right portion, that's not generally as much of a concern provided that rotating column of air is oriented horizontally. But what happens with convection, what happens in a thunderstorm, which causes that rotating column of air to tilt? Well, it's the updraft or the rising air into that thunderstorm cell. That updraft will take that rotating column of air produced by wind shear and it will tilt it. And if it tilts it far enough, it will tilt it vertically. And if it's powerful enough, you can have wall clouds, funnel clouds, and tornadoes. And we'll clarify what all of those are in a moment. Storm cells, of course, can be either single cell storms, they can converge into multi-cell storms, they can converge into quasi-linear convective systems, which is admittedly a nerdy way of saying a squall line, but since admittedly I'm a bit of a nerd, it's kind of cool to be able to say a quasi-linear convective system because why use fewer words when you can use more? But anyway, uh, you can have multi-cell storms from convergence of single cell storms, but you can also have supercells, and that's what we're going to be looking at tonight. These supercells, the most powerful thunderstorms, can produce wall clouds, funnel clouds, tornadoes. They often will produce intense rain, intense hail. They can produce straight line winds. They're just, they're not a good thing. They're best to be avoided if at all possible. So now that we understand what wind shear is with tornado genesis, let's look at the overall anatomy of a supercell storm. Well, beginning from the top down, we can see that overshooting top. As that convection, as that air is rising into the atmosphere, it will form often, it may hit like a layer of dry air or something and start spreading out, forming an anvil at the top. And that's actually one of the components that storm spotters will look at to determine the stage of a thunderstorm. They'll look at the characteristic of that anvil to determine, is this forming, is it intensifying, or is it weakening over time? Is it an older cell that is breaking apart and is diminishing? A lot of times, though, in these supercell storms, these mesocyclones, you can have convection so powerful that it just breaks right through that anvil and has an overshooting top. You can see over on the right, you have your mammatus clouds. You see that classic cumulonimbus cloud structure in the center. You can see, and you don't necessarily see this in real life, so to speak, every single time, but you can see over there down at the lower layer on the left, you can see that flanking line with that precipitation-free base, that rain-free base underneath. You can see those cloud-based striations, which we will talk about more in just a moment. Those inflow bands, as I prefer to call them, because that's a more helpful way to think about them. And at the base of those inflow bands, you can have your wall cloud. And at the base of your wall cloud, of course, as you can see there, you can have your funnel cloud, which if it's impacting the ground, if it's impacting land, is a tornado. If it's impacting water, it would be considered a waterspout. But obviously, as we know, things in textbooks, things in diagrams don't look as neat in real life as they do in textbooks, unfortunately. So let's look at an actual picture of that El Reno tornado, and of course attributed to the storm chasers that you see listed in the photo, Brian and Steve Koch, that they took as they were chasing this massive tornado at the time on May 31st of 2013. Here's the structure in real life of the El Reno tornado. And this tornado, this mesocyclone, was so large that obviously it's not even all within frame of this picture. But what can we see in this picture? Well, in the middle of the frame, you can see those inflow bands. They look sort of like stacked dinner plates. And in some photos, which you can easily Google, in some storms, you'll clearly see those striations better. In this particular photo, they're not quite as clearly well defined, yet you can still see them. And in real life, if you were to watch it, they would be rotating cyclonically. We'll get to cyclonic rotation in a few minutes. But those are your dinner plates, and those are indicating strong inflow, a strong rotating updraft. Over on the left, you can see your rear flank downdraft and your precipitation-free base. You can see at the base of the, in this case, a tornado cyclone as part of the larger mesocyclone. You can see the wall cloud, and at the base of the wall cloud, you can see the El Reno tornado, which I believe when this picture was taken, it was still in the infancy stages because it was producing multiple vortices and it would not yet turn into a massive 2.6-mile wedge with satellite vortices around the base. Just an incredibly destructive tornado and unfortunately killed some very prominent storm chasers at that time in 2013. You can see off in the distance that mesocyclone along with the tail cloud known as the beaver tail, which some storm spotters would mistake for a wall cloud, but it is in fact a tail cloud. Again, look for the rotation especially to determine if it's a wall cloud. That can indicate strong rotation, strong shear, strong updraft motion within the larger mesocyclone. And so the question is, if we were to see this in person, what components do we report then to the National Weather Service? Well, on a ham radio net, if you're using ham radio to talk to other operators who are observing the weather, you could report any of these things prior to what would be known as perhaps a red mode net or an emergency mode net, such as we call it here in Kent County. But the official components that we would report from this type of storm would be the wall cloud, the rotating wall cloud at the base of the mesocyclone, and the tornado. As well as I should add the funnel cloud, you still would report funnel clouds, of course, regardless of whether they have turned into tornadoes by impacting the surface or not. So let's just briefly look at these components in just a little bit more detail. So the National Severe Storm Laboratory identifies all these components, as I've previously discussed, as the official components, the important components for being able to spot these tornadic storms. Starting with the inflow bands, as I mentioned, those are indicating strong inflow to the storm. And with that rotation, you've got likely a strong supercell storm that is spinning up, literally spinning up. And we'll see this a little bit more easily once we look at this from 2 dimensions into 3 dimensions here. We have that beaver tail indicating rotation in the supercell. We have wall clouds, which will lower, of course, from the base of the storm and which have to rotate. If it's not rotating, it's not a wall cloud. It might be a tail cloud or it might be Scud, most likely. We don't want to report Scud NATOs, so to speak, which is just low-hanging Scud that's not actually rotating. We have the rain-free base, which is a bad place to be if you're ever chasing storms or you catch yourself in the midst of a supercell. What that's indicating is indicating a strong updraft motion pulling in all the rain-cooled air, so it's not raining there. Trust me, there's plenty of rain in these storms. However, the El Reno storm also produced some flooding as well due to the intense precipitation that occurred with the historic tornado at the time. We have the RFD, short for rear flank downdraft, which is what will produce the hook echo on radar. It's indicating strong downdraft motion on the rear of the supercell storm. And of course, your funnel cloud and your tornado, which really goes without saying at this point as to what those are. So let's actually take these things and just quickly identify it with another picture. Full disclosure, I don't know if this background image that I'm sort of using as the theme of the overall presentations here. I don't know if this is an actual photograph or if it's digitally enhanced or what it is, but nevertheless, you can still see portions of supercell anatomy here in this picture. You can see pretty clearly defined inflow bands, the striations, the stacked dinner plates as it were, which is indicating a strong rotating updraft due to the strong inflow coming into this storm. At the base of those inflow bands, we of course have our wall cloud. And at the base of our wall cloud, we obviously have a funnel cloud, which since it's impacted the ground is now a tornado and is kicking up a debris cloud. Now, wind itself, I should mention, is invisible. But because the pressure in these tornadoes is so low, it drops so low. I believe the current record was a 100 millibar drop in one of these tornadic storms. it will often condense. And so you'll see that condensation funnel, but not always. Don't take that as a guarantee for whether or not there's a tornado. But the condensation funnel, which you can clearly see in this picture, in conjunction with that debris cloud that you can clearly see as well being kicked up from the ground, that's obviously indicating, yes, indeed, that funnel cloud has lowered from the base of that wall cloud, has impacted the surface, and is now a tornado. And off to the left of the image, you can also see that rain-free base, that rear flank downdraft. So a fundamental question at this stage with tornado genesis is, why is it important to spot these? And I realize that question sounds very rhetorical. Well, we obviously know tornadoes are very dangerous, so of course we need to spot them. And that is true. But let's get into that and flesh that out just a little bit more. Spotter reports aid the National Weather Service in issuing tornado warnings. This means a tornado has been radar indicated or spotter confirmed, oftentimes both, and you need to take immediate shelter now. Now, for those of you who might be curious, the National Weather Service, to the best of my knowledge, does not always need real-time spotter reports to confirm a radar indicated tornado. For instance, if you see strong rotation, if you see strong reflectivity signatures, and you start to see a debris ball, such as using correlation coefficient, you don't have to wait for someone to necessarily see the tornado with their own eyes to say, yeah, we have a tornado on the ground, we need to issue a tornado warning. But all that to say, I'm certainly not diminishing the importance of spotting these storms. And I should add at this stage, because this is the most frequent question I get about my involvement as a SKYWARN member, is SKYWARN, at least officially on paper, is it about storm chasing, going out and looking for severe weather, or is it about storm spotting, reporting weather conditions where you are? And I would argue that, at least in terms of what is officially presented, SKYWARN, when properly understood, is all about storm spotting and not necessarily storm chasing. Now, there's nothing preventing you from chasing storms. As a free American, you can certainly do that if you wish, and that can be very helpful as well. In fact, I believe Muskegon County will utilize storm chasers who will watch storms coming off Lake Michigan. And I know in the past there have been discussions about, are simple storm spotters, so to speak, actually useful as opposed to those who will go out and deploy and become storm chasers. All that to say, at least from my own training and from my own personal choice at this moment in the stage of life I'm in, I don't chase storms, I spot storms. So I'll just add that in. So I'm not talking about the context of storm chasing here. I'm talking about the context of storm spotting. So storm spotting, especially in Michigan, is really crucial, especially in Kent County, because these tornadoes are not always easy to see. Sometimes they're nearly impossible to see on radar. So if you thought perhaps I was diminishing the importance of spotting these storms as they impact you, preferably you're obviously taking every precaution you can to stay safe from the impact of these storms. You know, don't be afraid that I'm attempting to do that, because, in fact, they are vitally important for what we will see, especially in part two. Now, prior to a tornado warning, a tornado watch can be issued by the National Weather Service. And of course, only the National Weather Service can issue these official warnings. No other agency can do that. Sometimes I have actually seen these tornado watches issued as far out as 24 hours or more in advance of squall lines, especially in the southern United States, or other tornadic storms systems that can spin up supercells. Now, I have seen this as well, not in our area, thankfully. It would be actually uncommon to see this occur in Kent County, but I have seen tornado emergencies declared. What is a tornado emergency? Well, this occurs when a National Weather Service forecast office will, in an extreme case, issue an emergency statement whereby a tornado, typically a deadly one, will cause significant injuries to life and limb and significant property damage. We're talking millions or billions of dollars in property damage. From what I have seen in my own experience, I typically do not see tornado emergencies issued only for radar indicated tornado warnings. These, at least to my knowledge, have always been in conjunction with actual spotter or chaser reports, just for those of you who are curious. But if someone knows otherwise, certainly feel free to let me know. In the case of the El Reno tornado, which is not the one pictured here, I'll talk about the one pictured here in just a moment. But in the case of the El Reno tornado and others, such as this Moore, Oklahoma tornado, which occurred, I believe, a few days, maybe a week or so, week and a half. I'd have to look at the dates to be entirely certain before the El Reno one. The National Weather Service has issued tornado emergencies and said if you are not underground and you are in the path of this storm, unfortunately, you are not likely to survive this storm, which, as you can imagine, is quite frightening and could certainly induce some panic, especially for those who don't know how to read radar very well or anything like that. As SKYWARN members, of course, we train in order not to panic at severe weather, but to be prepared for it and to be prepared and braced for the impact of it, and to warn our community members who may not be as prepared for it, and to assist in an amateur way the National Weather Service, who the professionals who are able to issue these warnings. And in the Moore, Oklahoma tornado, pictured in the upper right of the slide, this was an EF5 tornado that absolutely destroyed Moore, Oklahoma, as you can see in the lower right. Those are not fields that you're looking at in the lower right. Those are subdivisions. Those are neighborhoods. Even the grass is very difficult to see with how powerful this storm was, this violent wedge tornado, which completely leveled houses, killed people, injured many more, caused massive destruction, chaos, and heartbreak. Just a very, very violent and powerful storm. Actually, the last EF5 tornado to occur in U.S. history so far. And I would certainly be more than happy if it was the last one ever, but unfortunately, that probably won't be the case. Now, you might be curious at this point, I just used the term EF5. What does that mean? When we're talking about the larger context of tornado genesis, how tornadoes form, how you spot them, and so forth. Well, what it means, it's a scale. It's the official scale for determining how powerful a tornado truly is. Now, the EF scale is short for the Enhanced Fujita Scale, but preceding the Enhanced Fujita Scale, which was adopted in 2007, was the long-standing, simply known as the Fujita Scale or the F scale. And so, just to quickly break down the historic Fujita Scale, because many of the tornadoes that we're going to see in our state, our county watch forecast area in our county, were ranked under the Fujita Scale because they occurred, of course, prior to 2007. But an F0 tornado was a weak tornado that would produce winds approximately 40 to 72 miles per hour and cause light damage, such as damage to chimneys. It would, of course, break branches off trees. It would uproot some trees. It would damage signs and so forth. It might damage roofs and sidings and things like that, but it's not going to cause like houses to be swept off their foundations and so forth. F1 were also relatively weak tornadoes in the 73 to 112 mile per hour range. Now, I say that a bit tongue in cheek because I have experienced power outages with wind gusts around 40 miles per hour, and winds at 50 miles per hour can start doing some structural damage and start taking down some trees. So, 73 to 112 miles an hour is certainly not at all something to be taken lightly. Nevertheless, an F1 tornado typically would inflict moderate damage, such as peeling off roof surfaces. It could push mobile homes off foundations. It could also overturn them. It could move automobiles off the road. F2 tornadoes in the range of 113 to 157 miles per hour are where things really start picking up considerably, such as tearing roofs off from frame houses, mobile homes just being completely demolished, boxcars and trains being knocked over, large trees just being completely snapped or uprooted, light objects becoming projectiles. And that, I should add, the debris is what is usually the most deadly component of a tornado, which kills and injures the most people. It's not so much the wind, although certainly if it carries you aloft or slams you into an object, that could kill or at the very least injure you. But it's usually the flying debris which is the most deadly in a severe tornadic storm. Moving up to F3, again, strong tornadoes within the 158 to 206 mile per hour range, producing severe damage, such as tearing roofing off, such as destroying walls and well constructed homes, overturning trains, uprooting most of the trees in the area, lifting heavy cars and turning them into massive projectiles, really into missiles, would be the best way to describe them. F4, the same thing, 207 to 260 miles per hour under the classic Fujita scale at the time. Devastating damage, leveling well constructed homes, blowing structures with weak foundations some distances, throwing cars around, generating large missiles with large debris, sheet metal vehicles, large trees, pieces of housing, roofing, and so forth, all becoming large, deadly debris in the air. And F5, the most violent of the violent, we have 260 to 318 miles per hour, just unimaginable damage at that point. Lifting homes just completely off their foundations, scouring the ground to the point where it's difficult to even see the grass because of the debris, which is just gouging the earth as it's just being whipped along in these extremely violent storms, just disintegrating and carrying automobile sized, house sized debris in the air several hundred feet or more. Tornadoes at this scale have flung human beings in excess of half a mile. Obviously, they didn't survive it, but also, debarking trees, not only destroying the trees, but ripping the bark right off them with how violent and powerful the winds were in these storms. Now, I should add, I don't believe yet that there have been any confirmed wind speeds greater than 302 miles per hour, which was detected by mobile radar in the El Reno storm. I don't believe that that record has yet been broken. I believe that is still the fastest wind speed ever recorded on planet Earth so far. But the Fujita scale, as I mentioned, was eventually replaced by the enhanced Fujita scale in 2007. And why was it replaced? Well, it replaced the older scale in order to better estimate maximum wind damage. And this wasn't necessarily based on actual wind measurements from like anemometers or anything like that, but on damage indicators and specifically the degrees of damage that would occur in the damage path of these storms. Now, since the adoption of the enhanced Fujita scale, there have only been 14 EF5, the most violent of the violent tornadoes to date in the United States, with the last one being the Moore, Oklahoma tornado, which preceded the El Reno tornado in 2013. The Moore, Oklahoma tornado, which was pictured earlier, caused $2 billion in property damage, killed 24 people, and injured 207. And as we can see, an EF5 would be a 3-second gust over 200 miles per hour. Weaker tornadoes on the EF scale, going back to EF1, would be 65 to 85 miles per hour. EF1 would be 86 to 110 miles per hour. EF2 would be 111 to 135 miles per hour. EF3 would be 136 to 165 miles per hour. And EF4 would be 166 to 200 miles per hour, with EF5, as I mentioned, being over 200 miles per hour. That is an overview of the Fujita and later on, of course, the enhanced Fujita scale. But one thing I will add before we quickly look at how tornadoes appear on radar and then dive deep into the trends and statistics of tornadoes in our area would be tornado genesis in the context of a quasi-linear convective system. Now, as a disclaimer, I once heard a chief warning meteorologist, I believe would be the title, but a chief meteorologist at the National Weather Service office somewhere in Texas, there's a few of them actually in Texas, said, you're kind of a dork if you call a squall line a quasi-linear convective system. Be that as it may, that is the official terminology that the National Weather Service uses, and I will let others determine whether or not it is indeed truly a dorky term to use, but nevertheless is the term that I'm using in the presentation here. A quasi-linear convective system, or simply a squall line. A long line, typically a fast-moving storm system with significant outflow, meaning significant gusts out at the front of the storm, What are the characteristics of tornado genesis in the context of squall lines? Well, tornadoes in squall lines generally, but not always, they can be deadly as well, but generally speaking, they do tend to be weaker. But they are often wrapped in rain, which makes them much more difficult to spot and much more dangerous if they happen to be powerful, that is. And we're going to see that especially in part two. A lot of the tornadoes in Kent County arose from being embedded in squall lines. Now, another feature that makes tornado genesis more difficult to identify in a QLCS is that it can be embedded in straight line winds. So if you have a strong outflow boundary moving at 70, 80 miles per hour, and you've got an EF0 tornado in the midst of that, which is basically the same wind speed as that strong outflow boundary, you're not probably going to be able to tell the difference if you were visually looking at it, particularly if it's wrapped in rain bands at the time. And so squall lines, and I'll hammer this point home more in part two, need to be closely watched on radar. You can never take a squall line for granted in order to identify any tornadoes that are embedded within the squall line. So, having mentioned tornadoes appearing on radar, here's just a brief introduction before we head into part two later on. How do tornadoes appear on radar? We understand tornado genesis in terms of how they form and what they visually can look like and the implications of when they're embedded within squall lines. But on radar, how do they actually look? Well, this discussion could certainly take us much further, but the two features, the two signatures that I want to particularly point out would be the hook echo with reflectivity and the velocity couplet with velocity. So first, looking at the hook echo on reflectivity, I think it's most helpful to visually see what a hook echo actually is. You can see in the upper right hand image, you can see that tornado with that hook echo with that cyclonic rotation, which we'll talk about in the next slide when we get to velocity. But we can see here that larger mesocyclone. We can see that rear flank downdraft extending in a hook shape from the larger mesocyclone. We can see that area between the hook echo itself and the mesocyclone indicating strong inflow. We can see the hook echo itself, which in some cases, and I believe was the case here on this tornado, can indicate the size of debris and not simply the convection as well too. As you can imagine, this is a very powerful storm here that we're looking at. And in the lower right image, we can see how that's actually visualized in 3 dimensions. We can see off to the right that larger mesocyclone. To the left, we can see actually, because this is so large, we can see that tornadic cyclone connected to the larger mesocyclone at the top there. We can see that rear flank downdraft, which is producing a strong outflow boundary on the rear of the storm, producing that hook echo on radar being generated by that strong area of inflow, which combined with wind shear is producing that circulation within the supercell. And of course, that tornado and the debris accompanying that tornado is the actual hook echo itself. Now, there are other radar products which I've alluded to, such as correlation coefficient, which more pertain to, I believe, dual polarization radar. I will use that when determining debris size and so forth. But here, this is classic NexRad data, with the exception of the 3D portion, which is actually taken from GR Level 2 Analyst. But I think it's just helpful to look at the 2D image and see how it actually compares in 3D, like what this actually looks like, so to speak, in real life. So that's a hook echo, which pertains to reflectivity or how high convection precipitation in the atmosphere is rising, which will indicate its strength. However, and I believe equally, if not more so, helpful than looking at simple reflectivity is velocity. Velocity products will show wind speeds. And just as a quick reminder, green on a velocity product is wind going toward the radar, and red is wind flowing from the radar, away from the radar. Now, I've thrown around the term cyclonic before, cyclonic rotation. What exactly is that? Well, in the northern hemisphere, this is opposite, of course, in the southern hemisphere, but being located in the northern hemisphere, winds move in a cyclonic pattern that is in the direction of the Earth's rotation, or left to right, or counterclockwise. And in this image, you can see the clearly rotating tornadic winds known as a velocity couplet wrapping around Moore, Oklahoma. We saw images, photographs of this tornado earlier in the presentation, but you can see that strong counterclockwise rotation where it's extremely violent just to the southwest of Moore, Oklahoma on the map. So when you have these two products, reflectivity and velocity side by side, you can now see those signatures side by side. You can see that hook echo on the left, that large mesocyclone, that rear flank downdraft, that tornado producing the hook echo on the left. You can see those tornadic winds producing that strong, strong, strong velocity couplet on the right. Here is an actual radar image of the quote unquote quad state tornado, which occurred on December 10th of last year. It wasn't officially 4 states. It didn't break the tri state record because it did cycle at least once, according to the National Weather Service when they conducted an official damage survey. But nevertheless, in the upper left corner, you can see that strong hook echo and reflectivity. Upper right, you can see that strong velocity couplet. And the lower two products are really going beyond the scope of this two-part series, but nevertheless, they are helpful to know. And if you know how to use them, awesome, use them. If you don't know yet how to use them, I would encourage you to do so because they are helpful. We have the storm relative velocity in the lower left, which is also indicating the tornado. And then, rather frighteningly almost, in the lower right, we have that correlation coefficient showing that massive debris ball, which was just to the northeast of the town of Mayfield when this radar image was taken. I will and I realize, yes, it goes beyond my own responsibilities here for Kent County SKYWARN. But oftentimes, when I have the ability to do so, I will watch radar for these violent storms throughout the United States for two reasons. One, I personally find it fascinating to watch these violent storms on radar. And two, it helps me all the better understand how to interpret radar for my own area because what I see in my own area is obviously going to be less severe than this. Here we can see hail cores, we can see a violent tornado, wide debris ball, we can see tornado emergencies, multiple TVS's, tornado vortex signatures. So I'm just gonna throw that out there that if you have the ability to do so, watch other storms outside West Michigan and Kent County. It will improve your knowledge of radar observation in general. So we've looked at all of this at this point. As the final main category of part one, let's look at the history, the trends, the data of tornadoes that have actually struck our state, our county watch forecast area, and of course, our own specific county. Michigan is no stranger to tornadoes, unfortunately, with the tornado pictured in the upper right being one of the deadliest tornadoes in Michigan history. The deadliest tornado was an F5 tornado in June of 1930 that killed 116 people in Genesee County. The east side of the state tends to get more violent tornadoes than our side of the state, which is unfortunate for them. It is fortunate for us in that we're not as severely impacted by tornadoes as they are, but nevertheless, just interesting to point out. And in 1956, specifically April 3rd of that year, that's the tornado that you can see here pictured in the upper right of the slide. It was an F5 tornado known by different names because it went through Ottawa County and Kent County. Some called it the Hudsonville tornado, some called it the Standale tornado. But nevertheless, this F5 tornado severely impacted Ottawa and Kent County on April 3rd of 1956 in that it killed 14 people in Ottawa County. It killed 4 people in Kent County. It injured a total of 330 people, 200 of which were in Ottawa County, with the remaining 130 being in Kent County. And thankfully, while injuries have been dramatically reduced with early warning systems over time, tornadoes can, and they still do, cause injuries and deaths in our state. And I don't say that to exaggerate, I say that because it's factually true. Most recently, in our own county in 2014, a tornado sent 6 people to the hospital. Thankfully, not with life threatening injuries, but nevertheless, it did injure 6 people at that time. And we'll discuss that tornado more in part 2 of this series. And in St. Clair County, which would not be under the jurisdiction of the Grand Rapids office here, I believe that would be under the Detroit office. I would have to double check as to whether it's under the Detroit office or the Gaylord office in northern Michigan. But nevertheless, in St. Clair County, an EF1 tornado killed someone on June 27th of 2010. So I say that again, not because we panic over these things, but in order to be prepared over these things. But to really drive the point home of why we can't take these for granted, let's now examine an eyewitness account given by a resident of Standale at the time in 1956. She was a girl at the time. Maxine Baker presented an eyewitness account of the infamous 1956 tornado, the F5 tornado that killed 18 people, including, and sadly, including her mother. And she says this, quote, on April 3rd, 1956, there was a weather report, but not a watch or a warning, no radar or warning sirens. We didn't have those modern advantages back then. My father, Willard Brower, and I stood at the windows looking west. A big yellowish spot appeared in the churning pea green sky. My father said, "Oh, here comes the sun. It'll soon blow over." I believe the tornado was already approaching us, but more from the south and we didn't see it. We went to the living room, and as I recall, only a few minutes passed before our home was pelted with debris and all sorts of flying objects from the homes, barns, and greenhouses just across the road, or maybe as far away as from the declined farm, which was south and west of M21 and 48th Street. Then the windows exploded and doors flew off their hinges, and as I crouched on the living room floor, I saw a wall disintegrating as it fell toward me. That's all I remember until I crawled out from under some rubble. My father and sister were stumbling over the debris, trying to find me and my mother. My little sister was thrown far out into the fields, about 400 feet away from where my mother was found, although they were right next to each other in the upstairs bathroom when the tornado hit. My mother died from her injuries that night. Louise Roders Brower. In about 5 seconds, our house, barns, greenhouses, farm equipment, cars, and trucks were demolished. Only the foundations of buildings were left. It seemed like everything just exploded. We lost so many things, but it was the loss of those we loved and needed that was so devastating. Trying to rediscover who you were and where you belonged in the aftermath of that day was an ongoing dilemma for many, many years. We now have the advantage of a pretty good storm warning system, but many just ignore the warnings. I wonder if they would be able to get their family, friends, neighbors to a safe place in 5 seconds before the disaster hits. End quote. Friends, do not take severe weather for granted. If not, at the very least for your own sake, for the sake of your friends and family. That is why we train, that is why we prepare, that is why we do what we do, so that to the best of our ability we can keep ourselves and our families and our communities safe, and to best assist the professionals at the National Weather Service to be able to do their jobs, to generate these warnings, to understand what's going on, and to also, if need be, to assist emergency services in best being directed towards those who are most heavily impacted. I don't believe that this kind of experience would happen again, but let's not take Maxine Baker's experience for granted here. Let's not repeat what she had to endure. Looking at Michigan tornadoes by month from the years 1951 to 2021, we can see that Michigan has experienced a tornado in every month of the year, with the majority, of course, being April through August, with the most tornadoes, 264 to be exact, occurring in the month of June. The grand total for tornadoes thus far, up to the end of last year, 2021, was 1,192 tornadoes in the state of Michigan. 1,200 tornadoes in our state. You can look at the total tornadoes per year from 1951 to 2021. You can see a strong uptick in 1956 and a high number of tornadoes in the years 1970, from about 1970 to about 1980. Then there was a decline up until about 1985, where it picked up again until about 1992, where there was a very steep decline at the time. It picked up and it to a total of 24 tornadoes in 1998, where it declined back down to 6 in 2000. A huge increase, 42 tornadoes in 2001, again declined until the El Nino weather pattern struck around 2010, 2011. And then from about 2012 onward, we've been relatively consistent with the number of tornadoes across the state, with the exception of 2020, which frankly was good because, as we all know, 2020 had more than enough problems of its own, and we did not need a lot of tornadoes added to all of the issues going on in the year 2020. So, looking at some interesting statistics then from tornadoes across the state of Michigan, the most F0 tornadoes struck in 2001, 26 to be exact. The most F1 tornadoes struck and were tied. In fact, the total was tied between 1976 and 1977, 23 F1 tornadoes in both of those years. In 1974, the record for F2 tornadoes was met at a total of 19. In 1993, 9 F3 tornadoes hit our state at the time, the most F3 tornadoes that would ever strike. The most F4 tornadoes struck in 1965, a total of 14. And in 1956, 4 F5 tornadoes struck Michigan, the only time F5 tornadoes struck in our state's history. 4 F5 tornadoes struck our state in the year 1956, including the one that I gave an eyewitness account earlier. So as we look at Michigan tornadoes by now the more modern enhanced Fujita scale beginning in 2007, the previous graph being about the older Fujita scale at the time mostly, but also including some tornadoes from 2007 as well. We can see that predominantly speaking, EF0 tornadoes is what our state experiences the most, followed by EF1s. Uncommonly, we do get EF2 tornadoes, with one of them occurring just last year, as a matter of fact, although not in Kent County. And EF3 tornadoes are exceedingly rare, thankfully, in our state. We have yet to experience an EF4 or EF5 tornado in the state of Michigan. Looking at EF tornadoes by the statistics, the most EF0 tornadoes struck in 2010, again, that El Nino year, which spawned massive tornadoes in Tornado Alley, Dixie Alley, and so forth. But here in Michigan, 15 EF tornadoes struck in 2010. In 2016, 9 EF1 tornadoes struck the record for EF1 tornadoes in 2016, and for the state's history for that matter. 7 EF2 tornadoes struck in 2007. 3 tornadoes that were EF3 rated struck in 2001 and 2012 each. We have yet to have more than 3 EF tornadoes in any year in Michigan history. And thankfully, as I mentioned, we have yet to experience an EF4 or EF5 tornado. So looking now that we have looked at the entire state in terms of an overview, let's now look at the NWS Grand Rapids CWFA, which is simply the County Watch Forecast Area. CWFA is an abbreviation you will frequently see in their forecast discussions. It simply means the area for which the Grand Rapids National Weather Service office is responsible in the state of Michigan. And to describe the graphic on the right side visually, just to kind of break it down into 3 areas, the northern counties of the County Watch Forecast Area would be Mason, Lake, Osceola, Clare, Oceana, Newaygo, Mecosta, and Isabella. In the central region of the forecast area, we have Muskegon, Montcalm, Gratiot, Ottawa, Kent, Ionia, and Clinton counties. And then in the southern portion of the forecast area, we have Allegan, Barry, Eaton, Ingham, Van Buren, Kalamazoo, Calhoun, and Jackson counties. These are all the counties for which the Grand Rapids Forecast Office is responsible. And so now to look at the trends specifically within all of those counties going back to the year 1951. Again, following the statewide trends, we see a huge spike in 1956 from the previous years. We see a total in 1956 being 18 in the forecast area for the Grand Rapids office, as it was at the time. In 1965, we have 16. In 1967, we have 12. And then from there, it declined around 1970 before picking back up again, especially in 1976, where we had a total of 17, almost breaking the record at the time. Throughout the late 70s and into the 80s, tornadoes declined somewhat into the single digits before 1986, where we got back into the double digits with 11 in that year. And then it picked up in 1989 to decline again in 1990, only to pick back up again in 1991, and then to see a sharp decrease until 1995, picking back up again in 1996 and 1998, and declining in 1999 into 2000. But in 2001, we hit the record at a total of 19 tornadoes at the time for the Grand Rapids forecast area, and then again, we see this very regular pattern mirroring the larger state trends of increase, decrease, increase, decrease. In 2008, we had a spike of 11. 2016, we had a spike of 7. And currently, beginning in 2019, or really beginning actually last year in 2021, we have seen in the last 3 years or so an increase in the number of tornadoes in the county watch forecast area. Now, what will 2022 bring? I don't know. But climatologists are predicting a wet and stormy spring season, and so I would anticipate we will probably not, at the very least, see a decline in tornadoes from 2021. Looking at the yearly tornado damage going back to 1951 in the 70-year period, we see notably in terms of the millions of dollars of property damage that were inflicted by tornadoes. We see in 1967 over $28 million inflicted upon the residents of the forecast area. 1980, we see close to that same amount, $27.6 million. In 2007, we see a staggering $55 million of property damage occurring that year due to tornadoes. And then in Kent County in 2014, we would see over $2.5 million of tornado damage, and we'll cover that tornado in part two. But all that to say, as we look at tornado injuries, with the exceptions of the years 1956 with 200 injuries in Ottawa County and in 1965 from the Palm Sunday tornado in Kent County, we really don't see a significant number of injuries, thankfully. We do see a spike around 1980, but ever since that, it's largely declined, but it has not turned to absolute zero, as we can see in the years 2014 and 2015. Just very quickly, interestingly enough, that 1965 Palm Sunday tornado directly went over the current location where I am right now, my QTH to use ham radio terms. I admittedly was not alive in 1960. I did not yet then exist. And so I was, of course, not living in the damage path of the tornado at that time. But I'm glad that I wasn't, because if so, we would have been severely impacted because that Palm Sunday tornado tore right over our house at that time. We can see with deaths as well that, with the exception, unfortunately, of that 1956 year with that F5 tornado, we can see that deaths have sharply declined ever since the 1960s, with the exception of 1980, where we saw 5. However, for the most part, while they have been eliminated, they have not entirely been eliminated in the 2000s. We did unfortunately see 2 deaths in the Grand Rapids forecast area in 2007 and then 1 in 2008. Looking at the monthly statistics for tornadoes in the forecast area, we can see that they follow the same approximate trend as the larger statewide statistics, with June being the peak month for tornadic activity in the forecast area. We have not seen tornadoes in every single month of the year, thankfully, in the forecast area like the rest of the state has seen, but nevertheless, we can see that beginning in April, going through really the end of August, we see significant tornadic activity in terms of the overall count. we can see that June peaks with a total of 73 tornadoes in the month of June from the 70-year period between 1951 and 2021. There have been a total of 880 direct tornadic injuries in the Grand Rapids forecast area, along with 41 deaths, unfortunately. And there has been a staggering total of $166 million of property damage in the Grand Rapids forecast area, all of those counties that I mentioned earlier. Now, looking at the history of Kent County tornadoes specifically as we wind down part one of our two-part series here, we can see that most of the historic tornadoes on the Fujita scale were F1 tornadoes that struck Kent County, not surprisingly what you would think, F0 tornadoes. Specifically, just to break it down by numbers, we saw seven between the 70-year period 1951 through 2021. We saw seven F0 tornadoes strike Kent County, 13 F1s, 5 F2s, 1 F3, 2 F4s, 1 F5, and then as we switch over to the enhanced Fujita scale in 2007, 6 EF0s and 2 EF1s. We have yet to experience any tornado stronger than EF2 or in Kent County, thankfully. We have not experienced EF2 through EF5. And as we can see, these trends, these injury trends specifically for our own county, this one starting at 1956 rather than 1951. We can see that there were 130 in 1956. There were 142 from that Palm Sunday tornado outbreak that I referenced a few moments ago in 1965. And then apart from a few years between the years 1990 through 2021, there were no tornadic injuries in any of those years, with the exception of 2014 with an F1, or rather, an EF1 tornado that injured 6 people in that year. So thankfully, deaths and injuries are not what we need to most concern ourselves with, although we do not take those things for granted, even though statistically they have not occurred for some time. They still can, unfortunately, but nevertheless, they are unlikely to occur. The most likely occurrence from tornadoes is going to be property damage in our county. But there are exceptions to that, unfortunate exceptions in that in 1956 we saw 4 people die from the tornado I've mentioned before. We saw 5 of them die from that same tornado that passed directly over the area I'm now living in all these years later. We saw 5 die in 1965. There has not, thankfully, been a death in Kent County from a tornado in 57 years. Now, I know some listening to this are older than 57, so would have been alive in which death still occurred, but nevertheless, 57 years is a substantial amount of time, and thankfully there have been no deaths in Kent County in 57 years. And let's keep that trend going. We certainly don't need to add to that by having any new deaths in our area, certainly. Certainly wish to avoid that. We average here in our county 3 tornadoes every 2 years, or about 1.5 tornadoes each year. But there are again exceptions to these statistics in that between 2006 and 2014, we did not experience any tornadoes. But we have endured substantial property damage in the last 70 years, totaling $334 million. Most of that damage occurred, I believe, actually, let me correct the statistic. I believe it's 34. I believe there's an extra digit in my number there. I believe it's $34 billion, and most of that damage occurred in 1967 with the $25 million that was damaged from tornadoes in that year. So $34 million in property damage in our county cumulatively in the last 70 years. So thank you very, very much, folks, for your time and for your attention. Again, don't hesitate to email me or to leave a comment or question or feedback below. I very much appreciate your interest in these lectures. I have greatly enjoyed researching them and presenting the material. I will be very happy to see you back in part two. So with that, this is Colin McConkey to sign off as I would as a ham radio operator. This is Colin McConkey, KE8RXN. I will be clear. I will see you next time.